Today in class we talked about two different topics. We've been talking about weak acids and we kind of talked a little bit about weak bases. Now we're going to talk specifically about weak bases and then something called a salt. So we learned to do two different things today. One example of a weak base is ammonia, Nh3. Now, the weird thing about ammonia is it doesn't have a hydroxide. So if we were thinking about the Arrhenius definition, where is the hydroxide coming from? Because ammonia is a base. So when you have ammonia, you have to write water. And if you put ammonia in water, and if you think of water as HOH, hydrogen hydroxide, basically what happens is one of the hydrogens comes off of the water molecule and actually attaches itself to the ammonia. And when that happens, it technically makes ammonium hydroxide, but in solution, what it does is it gives you ammonium ions. So this was no charge, and it picks up a hydrogen, which has a positive 1 charge. So now it becomes a positive 1 aqueous solution, and then we get hydroxide. So there is our reaction. So anytime you have a base that you know is a base, you need to put it in water, and then you're going to break it apart. Basically take one of the hydrogens off. Ammonia products, or the hydrogen's going to go in the back. And then we have a compound called an amine. And what an amine group is very similar to an ammonia compound, but instead of having 3 hydrogens, one of the hydrogens has been replaced with a carbon group. So if we had something like this where it had nitrogen and it had 2 hydrogens, and I'm not going to draw it extremely correct, and it had a carbon connected to it instead of that hydrogen, this is called an amine. And when we get into organic at the end of the year, we'll talk a little bit more. This right here is our amine group. It's basically an NH2 group stuck on a carbon. And since this is 1 carbon, the prefix for 1 carbon is meth. And so this is actually called methylamine. It's also a base. And so we need to recognize when we have an amine group, so you're going to see a carbon and then you're going to see an NH2 if you saw something like this. And of course I'm drawing them out the organic way so you can kind of see it. Again, not exactly correct organic wise, but if you saw 2 hydrogens, I meant to say 2 carbons attached to it, the prefix for 2 carbons is eth. So this would be an ethylamine. If you had 3 carbons, it would be a propylamine, and so forth. These are going to be bases, and when you get into biochemistry and stuff, you start to see that more. So when we write these things, because you don't have a hydroxide, but they are bases, so all amines are bases. Because you don't have a hydroxide, you're going to have to put them plus water as well. And you're going to see the same thing. You're going to see the hydrogen coming off, and it's actually going to attach itself to the end of the molecule. So we'll go to our slideshow presentation where you'll see how it's actually written. And writing them is kind of the hardest part for some of you. It says many weak bases do not have hydroxide. This means that water must be included when writing the formula. Many weak bases contain nitrogen, such as the ammonia. Amines are related to ammonia where one of the NH groups is replaced by an NC group. And so here is the methylamine that we just saw. CH3 is the methyl, and then there's the amine. So if we were to try to write this equation, we would put it in water, and it's just like before, the HOH, and one of the hydrogens is going to come off, and it's going to actually attach itself to the end of the molecule. So you have CH3 now becoming NH3, but it's going to have a charge because it was a compound with no charge. It picked up a hydrogen, essentially a proton, and becomes a positive 1, and then water is left as OH minus. And then before in our conversation, we actually had talked about acids and conjugate bases, etc. So this is a good point to kind of review. If we know an acid, for example, we'll go with acetic acid. There's an acid. Well, its conjugate base would be the same thing with the hydrogen removed. So this is a conjugate base. C2H. So when we took that hydrogen off, we get that ion. So if you get something like hydrochloric acid, its conjugate base would be the chloride ion. If you get something like hydrofluoric acid, the conjugate base would be the fluoride ion. So you kind of got to understand that because we're going to be talking about acids and bases and sometimes conjugates, and being able to recognize, oh, that's a conjugate base, is going to be kind of important. And so that leads us to the next. Anions or weak acids are also known as weak bases. They're, for example, this is ClO minus 1. If we put a hydrogen on it, we would see that we would get hypochlorous acid, which is a weak acid. So because we know this is a base, we're going to put it in water. And notice what happens this time. Instead of the hydrogen coming off and going on the end like it did with these amines and ammonia, the hydrogen comes off and goes on the front. And we essentially get the hypochlorous ion, and then we get that hydroxide. Because this is a base part, not the acid, this is the acid, or technically the way this is written, this is the conjugate acid, and this is the base. When we did all this stuff here, so you kind of can think, because the arrows again are going both ways, so here's the acid, that's conjugate base, or vice versa. So we just need to start recognizing those anions, and if we stuck a hydrogen on it, would it be with a weak acid? So that's kind of important for us to write the equation, but we're going to see it Kb because that is the base instead of Ka for an acid. Whoa, wrong button. So now we're going to move forward. So it says calculate the pH and the hydroxide concentration of a 0.035 molar solution of ammonia. Now actually doing the problem itself is not hard. Most students really just have a hard time writing the equation. You have to know that ammonia is a base, so you're going to have to put it in water because there's no hydroxide. We're going to draw that double arrow. We're going to make ammonium and hydroxide. Essentially that water molecule is breaking up and the hydrogen moving. We're going to write it because it is a weak base. We're going to set it equal to Kb instead of Ka. Water is a liquid, and pure liquids we don't care about as far as, well, it's really important to have water, but as far as the Rice equation, we don't put pure liquids in the equilibrium expression. So you get 0.035 molar, you get 0, 0. Because these are all one-to-one. Don't you love this chapter? It's all one-to-one. You're going to add x. Don't get it comfortable because next chapter it won't be that way. And add x. We're going to subtract x. 0.035 minus x. And we'll end up with x squared over 0.035 minus x. And we're going to equal it to a Kb because of this hydroxide. I want to circle that so we can make sure we pay attention to that. Because anytime you have hydroxide floating around there, it's always going to be to a Kb, and that's going to be a huge thing in next chapter to know what to set it equal to. Alright, so we can get rid of our minus x. You could use solver, whichever you prefer. I think I did it both ways. You get really close to the same answer. If you scratch through your minus x, because this is to the negative fifth, you get 7.94 times 10 to the negative fourth. Or I think if you use solver, you get 7.85 times 10 to the negative fourth. I usually work it both ways. Now, if we follow x, one of the questions is what's the hydroxide concentration? Well, x, I don't know why I have those pluses there, but our x is our hydroxide, so there's our hydroxide concentration, so either one of those. And now to find the pH. Well, that's hydroxide, not hydrogen. So we have to find the pOH first by taking the negative log of our x and then subtract it from 14 to get our pH. And so our pH should be 10.89 or 10.90 depending. When you do this one you get 3.11 or 3.10 depending on which x you use, but really close to the same number. So not hard. The hardest part of that is actually writing the equation. Same thing with the amine. Same process going on. It's an amine. You have to recognize an amine is not an acid. So the hydrogen's not going to come off. You have to put it plus water. And what happens? The hydrogen goes to the end. Oh, I already put that hydrogen on the end. Did y'all see that? Let's get that little 2 in there. It was a 2. It picks up a hydrogen, becomes a 3, and then it makes that hydroxide. It's going to rise just like, so again, these aren't really any harder. The hardest part is writing those equations. So 0.075, these start out as 0, we subtract x, add x, I meant to say, add x, subtract x on this side. Always where your 0 is, you would add. So we end up adding x squared over 0.075 minus x. We're going to set that equal to Kb because of this hydroxide. And so then this would be 4.4 times 10 to the negative fourth. Negative fourth a lot of times isn't very safe to use solver. I think this one would have been okay. I mean, it's always safe to use solver, but not okay to scratch through your x. I think I used solver and did it the other way, and you actually get about the same answer. I got 0.00, and there's only 2 sig digs in this problem. So there's my molar. That is your hydroxide. So that is your OH concentration. So you can find the POH by taking the negative log. And then your POH, I got about 2.26. So your pH is 11.74. So it's actually pretty high pH. You could find your percent ionization if I asked. You could take this x divided by that I times 100 to get your percent. Same with this one up here. We could take our x divided by I times 100 to get our percent. So that's pretty much all there was with weak bases. And then we move on to how in the world is a Ka and Kb connected? Well, Ka stands for the ionization constant of an acid, and this is the ionization constant of a base. If you multiply those together, they equal Kw. Kw is 1 times 10 to the negative 14. That's going to be a very useful. I know some of you didn't use the hydronium times the hydroxide. Equals 1 times 10 to the negative 14, but you will use this quite a bit. Alright, if you think back to last chapter, the bigger the K got, the more it favored the products. So if we had like A plus B making C, and a K was like 2,000, that means it really favored, at equilibrium, favored C. If we had a K of like 0.02, then it kind of favored this way. Well, if we start talking about acids, their K is talking about how well they break up. So if we talked about HX, just some random acid breaking up, and we said that it had a K of 20, and can't even write an H, HY had a K of 300. Well, this one's favoring breaking up more than this one's favoring breaking up because it's a larger K. So you can actually tell which acid is stronger by looking at the larger K value. And it says given that the Ka for hydrofluoric acid, which is HF, is 6.8 times 10 to the negative 4th, and that hypochlorous acid is 3.0 times 10 to the negative 8th, which is a stronger acid. Well, the stronger acid is the one with the larger Ka, and this is a larger, so therefore that is a stronger acid. Bigger the K, the stronger acid. Strong acids like hydrochloric acid and stuff, they'll reach equilibrium, so they don't have a K value, but they're very strong because they break apart all the way. I keep hitting the wrong button. So now when we go to the next one, we'll write the conjugate base for each acid and calculate the Kb. Well, this was our acid, so this would be its conjugate base, the fluoride ion. To calculate the Kb, I would take 1 times 10 to the negative 14th divided by the Ka for this one. And we would find, I gotta switch the page, that this equals 3.3 times 10 to the negative 7.